Alright, so we're going to look at some properties of shape functions. And at last class, at the end of class, we developed on the board the methodical process for developing these shape functions. We did it for a linear and a quadratic. And then yesterday I posted a screencast that showed how you would do it in Mathematica step by step, develop the shape functions for a quadratic element. Okay. So what I did here, what I have here is I wrote a function that will actually develop the shape functions for me for an element. So what I do is this is a function. The first argument to that function is the number of nodes I want. So if we're considering an element like we have here, we have 2 nodes, and then the second one is a vector that represents the domain of the problem. So if we say 0 to L, there are 2 shape functions. Okay. We could also say, coincidentally, this distributes the nodes equally over the domain, but that's not a requirement. That's what this function does. So, but I could also say minus L to L. The domain does not have to be uniform, so I could say minus L to L over 100. And it's going to give me some funny looking shape functions, but it doesn't matter. I can also add more. So if you go out and you watch the screencast, you'll see that I developed the shape function, a 3-node element. The shape function is for a 3-node element over the domain 0 to L. So if you notice now there's 3 shape functions. There's one, and there's one. Okay. You can also space that over. Sometimes you want the coordinate system to be in the center of the element. So that would be your shape function. And what I want to show is that if I put total on the end, it's just going to sum up everything that's in there. Okay? It's always 1. So it doesn't matter if I change this, reevaluate it to 4 or even 10 terms, or if I change the limits, the shape function is always summed to 1. Okay? Partition of unity. So let's look at something else I put together here that actually shows if we consider the shape functions defined over a domain from 0 to 1, if we have 2 terms, 2 nodes over the element, that's this element here. This is what the shape functions look like. So the first shape function is this, and the second shape function is this. And if you'll notice, they're exactly what I said. The first shape function evaluated at the first node is 1, and evaluated at the second node is 0. The second shape function evaluated at the second node is 1, and the second shape function evaluated at the first node is 0. Okay? If I add terms, so I'm going to add a term. Now we have 3 shape functions. Again, the first shape function evaluated at node 1 is 1, at node 2 is 0, at node 3 is 0. Second shape function evaluated at the first node is 0, second node is 1, third node 0, the third shape function, first node 0, second node 0, third. Okay? And we can add more terms, so there's 4 shape functions, 5 shape functions. It begins to get untractable. You can't really follow where all those lines are going. But what you can see is there's a lot of lines that cross at where the nodes are. So every time I add a term, I'm adding a node. Again, we're dealing with a single element. But you can see here there's 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes here. Okay? And I take it all the way up to 10. But all of those shape functions have the same property in that the first shape function defined at the first node is 1, it's 0 at every other one. Second shape function defined at the second node is 1, 0 at all the others. Okay?